My name is Alex, and I'm going to talk today about symmetry detection and Beck in cost-optimal planning. This is a joint work with Kuroiwa and Chris Beck, and let's begin. So, given we are in HSD, I assume basic familiarity with the R formalism. For those who, for some reason, forgot what it is, we have a finite set of variables. Each variable has a finite domain. We have a finite set of actions that change those variables. We have an initial state, that's where we begin, and we have a goal description that describes the goal states that we would like to reach from our initial state. Usually we look for a plan. Optimal planning means that we look for an optimal plan, which is a sequence of action from the initial state to some goal state. Okay. So symmetry detection and Becking is one of the methods to prune states that are undesirable and to ease the search effort. It was done for model checking by Emerson Stills, Rinton did it in SAT, Fox and Long did it for heuristic search planning, then Beck, Zor, and Rosenstein. And afterwards, there were Dom, Schlakatz, and Shleyfman that did it for classical planning. And this is basically the methods that is used today. There are actually two methods, we describe them later. So how it's done? You take a formal representation of your task, say FDR, you construct a problem description graph, which is a colored graph. You compute the symmetry group of this graph. You take the symmetries, you map them on the symmetries of the transition systems, and you use the symmetries in the transition system to prune states that can be pruned while still preserving the optimal plan, at least one of them. That's the point. It performs quite well, both theoretically and empirically. So what is the problem description graph? Because that's the main focus of our work here. So suppose you have a problem, you have a truck, you have a package, you need to make a delivery from point A to point D. The actions would be load the package on the truck, move the truck to D, unload the package. I assume we're all familiar with that. So let us construct a PTG. We have two variables. T stands for truck, P stands for package. Each variable has its values, so track can be in 4 locations. So it's A, B, C, D, different colors for variables and values. Package can be either in A, B, C, D, which is a goal location, and package can be graph, and we have actions. We can start this graph. This is a small graph that is in the size of the task representation. Compute the automorphism group, symmetry group of this graph, use it to break symmetries and standard methods. Okay, we would like to take this and we would like to extend it to numeric planning. So why? Say we have 2 tracks, and now, except for locations, we have such parameters as fuel, truck load, package weights. This is all numeric parameters. And we would like to account for this. To this end, we have the formalism of numeric planning. I'll address it in the next slide. But the point is, we would like our symmetries to account for numerical formulas. And that's what we will do here. So numeric formalism for FDR is basically take FDR, add syntactic numbers. So now we have 2 types of variables: classic variables, which mean finite domains, and numeric variables, which mean numeric domains. Preconditions and effects also have classical preconditions and numeric preconditions, effect of classical effects and numeric effects. The initial state is a state, a full assignment of variables. Goal condition, once again, classical conditions and numeric conditions. So what are numeric conditions and numeric formulas? We just take a linear formula in the numeric variables, its linear numeric variables. We can assess its value in each state, which means assigning to each numeric variable this variable, the value it has in the state. And we can either create a condition out of it, out of a linear formula with a constant, you can just compare it to 0. Or you can make an effect, just add it to the variable in the next iteration. So in the next state, it will be the value of last state plus the value of the numeric formula. Overall, this formalism is proven to be undecidable, but we still try to manage, make something of it. So a special case of this formalism we call simple planning. In simple planning, we still have linear conditions, but here we don't have the linear formula. We can add only constants. Even if we add only constants, it is still undecidable, but well, that's life. So our plan is as follows. We define numeric structural symmetries. This is done in the paper. Due to the limitations of the medium, I won't be able to do it here. We show that numeric structural symmetries can be embedded into the transition system graph. We construct a numeric PDG. That's what we will do here. We theoretically show that the group of the numeric PDG is equivalent to the numeric structural symmetries. We compute the group, and then we run it on the transition system to prune states using the standard algorithms like DKS and OSS. Bonus, on the way we show that computing NSS in the way we do it is GI complete, which means it's equivalent to computing whether two graphs are isomorphic or not. So let's see. So here we have a numeric PDG. So VP is a classical variable. It has two values, false or true, and that's the standard PDG. What we do for numeric variables is as follows. Instead of recording their values, we record their multiplication constants. So if we have a linear formula, x greater than 3, for example, as a precondition of action A2, we take x, its multiplication, here multiplying constant, it's 1. To make the standard, we move the 3 to the other side, so we get -3. We introduce the v0, which is basically a demi-variable that always equals 1. And we compare both of these, their sum to 0. Since summation is commutative, we don't really care about their order, right? So here we represented this formula, and then we put it as a precondition to A2. The same goes, for example, for y less or equal to 0. Take -1, multiply it by 1, compare it to 0. The linear numeric effects follow almost the same pattern, but here we have an additional edge that usually effects are represented by an outgoing edge from the action node. But here, to represent that, we take the 3 plus x times 2, and we assign it to y, so we add an additional edge that leads from the plus equals operator to y. Note that all linear variables can be represented as plus equals operator. If we have minus equals, we just multiply everything by -1. So once again, if we have a goal condition, say here the goal condition is 3y greater or equal than 7. Once again, take the semi, whatever variable that equals to 1, multiply it by -7. Take y multiplied by 3, add them both together, compare them to 0. If they're at 0, this is a goal condition. Okay. So we prove that this actually syntactically captures the structure of the problem. So what we do then, in theorem 3, we showed that the NSS and the group of NSS and the group of morphism on PDG are isomorphic. We map the PDG group on the NSS. We show that the NSS can be embedded into the group of the state transition system, and we use the symmetries to prune stuff. Now, one of the problems here is the larger group here is not necessarily finite. And it may have generators, if you know what it is, of an infinite order. So the computing larger symmetries and that are not syntactic seems to be like a really hard problem, but this is still a thing to explore. So let's move to the experiments. We run the two algorithms, DKS and OSS, compare them to A star. Usually, orbit search performs better than both DKS and A star. DKS expands less states, but the states of DKS are larger due to the hash function than those of orbit search. And we get slightly better results. So can those be improved by, say, smarter local search of virus optimization? I think they are, but this still remains to be shown. So lastly, I would like to say that usually I put here a cute picture of a symmetric animal that's a represented finite symmetry group, but when we have numbers, the symmetry groups are now not a finite object, but instead can be seen as patterns. So how we analyze patterns in numeric planning is remain to be explored. Thank you, and let's move for questions.